representation, and the problem statement we are seeing today is counting bits. The question is, given an integer n, return an array answer of length n plus 1 such that for each I 0 to n, answer of I is the number of ones in the binary representation of I. So example, if they have given 2, for each index 0, 1, 2, we have to write the binary representation and return the number of ones in the binary representation of that index. So for 0 there are no ones, for 1 there will be 1 1, and 2 also there is 1 1. So we have to return 0 1 1. Similarly for n equal to 5. So how do we solve this in a brute approaches? This is the C++ code. Now example, if we take n is given as 5, these are the index we have to find, array of index. So for 0 to 5 we have to iterate firstly. Now sum will indicates the number of ones. So sum is a flag, sum we have to initialize it with 0, so it keeps the track of number of ones. Then num is the index, so we will update the index to num. So num will be 0, then 1 2 3 4 5, and always for 0 it will be 0, there are no ones in it. Now coming with 1, what we do, what is the logic here is, this first %2 will give the number is odd or even. Basically the last bit, whether if it's odd it will be 1, if it is even it will be 0. So this we will find, we will add to sum and we discard this bit. Similarly again, this we will find the last bit 0 or 1. If it is even 0, odd 1, we will again add to sum and discard this. So basically we will be left shifting this. Well, left shifting means by 2. So that's what. Now for every index here, now for every num, now num is here, so until this becomes 0, we find the last bit, if that divided by 2. So if it is odd it will give 1. Basically if there is 1, that returns 1, and that will be added to sum, and we left shift is by 2. We remove this. Again here it will be 0, this is 0, so before it was 1, 1 plus 0 0, then remove this again. So this process repeats. So for 1 it is like this, then num will be updated to 2. So for 2 also we do the same. First here by 2 will if we do num by 2, then this is 0, this will be updated to sum, we discard this, then again this one, we discard this. So we left shift all the bits and find the last bit if it is 0 or 1, and we update it to sum. So this happens with the entire indexes. So it is a while loop inside a for loop, and at the end we at the end of each while loop we just push the sum. So what will be the time complexity for this? Now firstly we are running a while loop inside a for loop, and this while loop, for this number of times num equal to num by 2 and number of bits 3 bits. So for that the time block complexity will be log 2 of I, number of bits will be this bits. So how many bits are there? That many times you will be doing by 2 times. That's why log, if that was by 2, that's why we do log. So for each this index we get log 2 of, if it is 32 bit 32, 64 64. We do this, and how many times we are doing? N times. How many? They ask that n into that log of 32 or 64. As it is a for loop inside a while loop, we are doing that many indexes, right? So we get n into log n times time complexity. And space complexity we only used extra this array, so space complexity is big O of n, time complexity is n log n. So this is a brute approach, we have to solve it in a better way. So the best approach will be dynamic programming. It sounds big, we can discuss depth in another video, but I'll just give a brief approach of the simple problem. How do we do this? Forget about DP. Just we'll see the pattern, how it is going. Now for this 5, just a second. For this 5, what are we doing? Now while calculating 2 itself, we were doing 0, then if it is the last bit is 0 or 1, discarding, and finding for this, right? Then again discard, do it. So basically instead of doing this again and again, now we have this example. Take this only. This was the last bit, 0. If we discard this, and we were counting for this, basically number of bits. What is 0, 1? This is 1. So we already have counted for 1. Then again, why are we doing this? Okay, so in a better way, now take for index 5 only, 1, 0, 1. Now this is the last bit which we get by %2. So a %2 we are doing, and we are finding for this remaining value, right? As we discard this, the by 2 of this, we are looping again this whole thing. But in previous iteration in the for loop, we already have found for this value, which is 1, 0. For 2, we already have found how many number of bits are there. So why we have to repeat the process when we already know for 2 we already would have got 1? So if we store this somehow, directly we can use this and the last bit, right? We can use the memory of this and this last bit, which we are, if it is odd, we can do 1. If it is even, just adding with 0. So that is main DP comes into picture. Instead of repeating the process multiple times, we store it in a way and we use it. So for this example, now same example, 0, 1, 2, 3, 4, 5, and if we write in a binary representation, this is this. So we just need to find removing 1 bit, whatever the memory is there, and the last index. Removing the 1 bit means that is by 2, left shifting. So first, what is the I by 2? This is the I by 2 value. 1 by 2 is 0, 2 by 2 is 1, 3 by 2 is 1, 4 by 2 is 2, 5 by 2 is 2. I by 2 value. And I percentage value, reminder, if it is odd, then 1, if it is even, 0. Now, if you take the count of these two, this is the values, okay? So, first, number of ones in 0 will always be 0. This we already know. Now, to find 1, which is this one, what we do? The last bit is even or odd. This is odd. So, I percentage 2 will be 1. So, this is the I percentage 2 value. And this is 0. 0 already we have the count. So, T of, instead of writing 0, we can replace with T of 0. So, T of 0 plus 1, 1. So, 1 is the number of ones in this. This we got. So, T of 1 value we know as 1. We already have stored it. Now, T of 2. So, T of 2, what is T of 2? 0, 1, this. Basically this. If it is even, this is 0, I percentage 2 equal to 0. And this one. And what is this? This is T of 1. So, T of 1 we already know. That will go here. T of 1 plus 0. That will become T of 2. So, similarly for T of 3. T of 3 is this one. This is T of 2 plus the last bit. Same. I'm sorry. 0, 1 is T of 1. So, T of 1 plus the last one. Next, 4. 1, 0, 0. This is T of 2 and 0. 5. T of 2 plus 1. So basically we are storing this value. Instead of finding now for 5, example removing that and finding again for 2, we already have the value of 2. We already did count the number of bits in 2. So directly we are using that and the last bit. So by this approach, we already, solve the most of it, right? We are not redoing the things. Same, that's what, left shifting by 2 and the last counter will be increasing like this. So storing this in table format like this is tabulation. So this is approach in DB where we store in a table, that is called tabulation. And how are we getting from 0th value? First we find 0, then 1, t of 2, t of 3. We are doing from the basic level, right? From bottom to upward, I'm telling is. So bottom to up approach we are doing. So we are finding the least value to the what desired value we want. So 0 to n we are going. So this is a bottom up approach. And here we just need to calculate only one, like n times, right? If it is 5, already we would have done for 2, then for 1, like this. So for 4, only one time we are doing, so that will be big of n. So we did from n log n, we go of n log n to n, and we have, this is the best time complexity, and space it will be the same as we are using t of n plus 1. This is like as we need one space, this is the space complexity, so big O of n. So now let's see the C++ code for this. So this is the C++ code. As I told, t of n plus 1, we need one extra as we have 0 index. So t of n plus 1 we store in a vector. Then t of 0 will always be 0, and we'll start with 1 till n and we iterate. So t of I will be storing in that itself. So t of I will be t of I by 2 plus I percentage 2, if it is odd or even, based on another one. And we return the t, directly the array. So this is the approach. Thank you.